Good morning again. I'm a research fellow here and also a non-research fellow at University College London. It's a really privilege to chair this day. So our first speaker is Geoffrey West. Geoffrey West is a theoretical physicist, and he's mostly famous for his work on unified scaling laws and also quantitative predictive science on cities, companies, and global sustainability. And I think during one of his last talks here, he very nicely summarized his research as a search for unifying principles and simplicity underlying complexity. Professor West is a distinguished professor at Santa Fe Institute and a former president there. He is also associate fellow at Oxford University and a visiting professor here at NTU. He published several books, and the most recent one, Scale, was published just last year. It's a marvelous book. I recommend everyone, and well, it's not just me. New York Times also recommends it. Without further ado, let us welcome Geoffrey West.
Thank you. This has a slightly grandiose title. I'll have to explain what universal means because it doesn't mean quite universal in the usual sense. Can everybody hear me, by the way? There was a little problem with this microphone earlier. Everybody can hear? Good. I really enjoyed both the introductory talks, and as you will see, some of what I have to say at least relates quite directly, and some less directly but implicitly, to what both Peter and Jan were talking about. And I come to it as a physicist, so it's not a qualitative description, but I'm going to, even though the way I'm going to present the talk is almost entirely non-technical. There's once or twice I throw in an equation, but mostly it's going to be non-technical. But underlying it is a lot of mathematics and a lot of physics ideas and biological ideas and social ideas. So, like Peter said, I guess, when this was presented to me, I thought, Jesus Christ, complexities of time. That's quite a challenge, actually. And I have a sort of dictum, actually, that I only like to talk about things I actually know about. So as you will see, for those that have heard me talk before, I have carefully manipulated this so that I can give my usual talk under the rubric of complexities of time. But it actually relates quite directly to what's been said. So the first thing you think of, at least I thought of when I thought of complexities of time, is, of course, what's the simplicity of time? That we should first discuss, at least briefly, at least remind ourselves about the simplicity of time. Well, the simplicity of time, certainly in science, but is also sort of our intuitive understanding, was formulated by Isaac Newton, famously, in which he said, as you can see, absolute true and mathematical time in and of itself and of its own nature, without reference to anything external, flows uniformly. So this is quite different than most of everything that was said in the last half hour. And then he says, relative apparent time and common time, so he already recognizes there is something different about the way we perceive it and use it, is any sensible and external measure of duration by means of motion, linking it with motion, such as a measure is commonly used instead of true time. So indeed, that gets expressed in equations in some trivial way, just as if this is Newton's second law, in some trivial way where this t is time, and that incorporates everything about time. And the astonishing thing about this is that by doing this, everything that you have technologically around you and you use in this whole society actually derives from this kind of thinking, which is amazing because it's at odds with one's sort of daily feelings about time in the sense that was just described. And indeed, this is related to understanding planets and satellites and all motions around us, and we invent things like this to remind us that time is linear and precise, and we follow its rules, so to speak. And even more, something that I resist extraordinarily is to make it truly linear by making it digital instead of going at least round, which says something about what time is actually about. So this is what Newton had said, and the question is, what is the relationship of that to the complexity of time? Represented, here's a famous Salvador Dali painting, where the clocks have obviously a highly nonlinear aspect to them. Or this, which I found somewhere on the web, which is pretty much what the last two speakers said. Definition of time: slow when you wait, fast when you're late, deadly when you're sad, short when you're happy, endless when you're in pain, long when you feel bored. Sometimes time is determined by your feelings and your psychological conditions, not by clocks. That pretty much says it, actually. The question is, can we actually put any of that into some more scientific framework? So I'm going to go somewhere in between the simplicity and complexity in the way it was discussed, and I'm going to address it through a bunch of questions that involve time. One is that we're very well aware of. We stop growing. Time. We grow and we stop. Why do we stop growing? Why do we die? Why do we live 100 years? Where does 100 years come from? Why isn't it 2 to 3 years like a mouse, which is made of exactly the same stuff as we are? What happened here? This is a measure of time. This could have been used as a measure of time. You know, I mean, it's not a precise one, but there was something that happened during time. And I will come back to this. A remarkable fact that all mammals have approximately the same number of heartbeats in a lifetime. And I will come back to this. So almost as if it's Newtonian. There's something that's beating there in the background, and we all sort of follow along with it. Another time thing. You spend a third of your lifetime asleep. Where and why? Why is it 8 hours? Why isn't it, what I wrote down here, 15 or 16 hours, like when you were a baby, or like the little mice that run around, or just 3, like an elephant? So where do these sort of time scales come from? Thinking of longevity, why is it that all companies die? You know, soon there won't be, soon Google will disappear, and Microsoft and so forth. Why do they all disappear? Why are they so fragile? And yet, most cities, almost all cities survive. As I often say, you can sadly drop atom bombs on cities, and 25, 30 years later, they're just fine. But a little wiggle of the stock market, and you lose things that seem invincible at the time, like TWA and Lehman Brothers and so on. So companies are fragile in terms of their lifespan, their lifetime, and cities tend to be open-ended. So there you are. There's a few examples. So why do they keep growing? And why is it, we're already referred to, that the pace of life seems to get faster and faster, which indeed it does in terms of socioeconomic time? And if that's true, is any of this actually sustainable? And the last big question is there an end to time, and in particular socioeconomic time? All this marvelous process that we're all engaged in, is there a finite time to that? So if I have time, I will try to address some of these questions. So in deference to Stephen Hawking, who died last week, I guess, I resurrected a quote that some of you are very familiar with. So at the turn of the millennium, Stephen Hawking was interviewed, and he was asked this question. Some say that while the 20th century was the century of physics, we are now entering the century of biology. What do you think of this? To which he answered, brilliantly, may I say, something which I wholeheartedly agree with. I think the next century will be the century of complexity. Hence the complexity of time. Okay, so complexity. I'm not going to discuss complexity. I'm just going to give a laundry list of many of its attributes. You can read them. It's got huge numbers of components, lots of cells, lots of people. There's many different time scales, but also spatial scales. It's usually highly nonlinear. There's sensitivity to boundary conditions. You diddle here, and there's a big change over here. There's lots of emergent phenomena. One of the things I'm going to talk about is emergent time. There's usually unintended consequences, but one of the most important aspects of these systems, of course, is that they are continually evolving and adapting, and they are therefore typically historically contingent and path-dependent, involving a concept of time. And the thing I'm interested in is this. Is there any simplicity underlying any of this? So as I said earlier, I'm a physicist, which means I don't like to talk qualitatively. I don't particularly like to bullshit. I like to search for underlying laws and principles leading to quantitative predictive framework, if that is at all possible. And can we apply this to this kind of question? And so the first question you might ask, could there be Newton's laws of these things? You know, that is precise laws that give rise to precise predictions, such as the movement of the planets around the sun, or more relevant to us today, maybe, is the movement of satellites so that we can use our bloody cell phones. We can do those to extraordinary precision, but obviously the kinds of systems we're thinking of here that have this complexity of time, not only is it unlikely, I would say impossible, that one would have that. So we won't have a theory if we want to apply kind of a physics paradigm, but what we could have is maybe what I would call a coarse-grained description, sort of on the average, aren't the kinds of questions I asked a moment ago, but giving quantitative answers about average quantities. So I'm being able to understand why everybody in this room will be dead in 100 years, but not being able to predict in detail the lifespan of any individual, except possibly, maybe in some statistical sense. And the idea is there is a highly coarse-grained, low-resolution theory, and that maybe with that, one can iterate to get something with increasing resolution and greater granularity and greater quantitative predictive power. So that's the idea. So this is the spectrum of things I'm going to touch upon. From the molecular time scales, microscopic time scales, that cartoon at the top is something called the respiratory complex. It's the little engine inside you that produces ATP, your currency of energy. And there's about 500 of those little engines in each mitochondrion, which is that potato-looking thing on the right, in the middle there. And there's about 500 of those in each one of your cells. I mean, it varies with the type and so on. So there's almost a million of those little engines in each cell. And there's 100 trillion of those cells inside your body. And each of these has their own time scale and their own structure. And all of those 10 to the 14th cells have to get together to make coherent objects like this, and do the kinds of things we're all doing in this room, moving and doing, and so on. It all has to be extraordinarily integrated, despite the fact there are extraordinarily different time and spatial scales. And we have to then get those things together to produce structures like this, and ultimately like this. So there is a sort of a direct connection between that and this, amazingly, and that involves both spatial and time scales. Okay. And all of these have, these very generic properties associated with them in one way or another, and all of these do involve time scales. So I'm now going to talk a little bit about biological time, and I'm going to do it first by talking to you about something that some of you here, I know, must be bored stiff, having seen and heard me talk about this part of it anyway before, so turn off, doesn't matter. So here we're one of these. This is us. We're a mammal, and we span a range of 8 orders of magnitude, 100 million in mass, from the shrew to the blue whale. And each one of us, of course, has evolved with our unique evolutionary history. We look different. Each sub-part of our system, each organ, each cell type, each genome has its own unique history. Everything is, of course, historically contingent. And so naively, at the most naive level, if you were to ask anything about either time scales or spatial scales in these things, you would expect there to be, if you plotted some physiological variable on the y-axis against the size, you would see great scatter, tremendous scatter, because the scatter would simply be reflecting the historical contingency and its own unique historical natural selection path. And that is exactly what isn't true. This is what is true. This is the data. And this is the most fundamental quantity, of course, of any organism. And it is a time. It's a rate. It's the rate at which you use energy. You need energy to stay alive. And it's plotted logarithmically, so you get a mouse and an elephant on the same graph. And what you see is extraordinary regularity, a very simple straight line underlying what is perhaps the most complex physical process in the universe, metabolism, creating life. So the other aspect to it is that not only is it linear on a log-log plot, but the slope is less than 1, which means that there's an extraordinary economy of scale because, forget about natural selection, the most naive thing you might have thought, if you hadn't even thought about it at all, would be if you double the size of an organism, you double the number of cells, therefore you double the amount of energy that's needed, which would mean linear, which would mean the slope of that would be 1. The slope of it is actually 3/4, which means every time you double, instead of needing twice as much, you only need, roughly speaking, 75% times as much. I'm afraid I have to go through all of this in order to come to the question of time, but you'll see where it's going shortly. So this amazing scaling law is not just this bunch of animals, but it turns out it's across all organisms, including plants, trees, fish, insects, crustacea, whatever, even down to the cellular level. This is that same line. This is drawn in. That red line is exactly 3/4, just drawn in. And there's data on the metabolic rate of bacteria all the way down to, in fact, the respiratory complex that I showed earlier. And so we have this sort of generic law that seems to follow over 27 orders of magnitude that this is the mathematical way of saying that slope is 3/4. It's a so-called power law, and metabolic rate scales with the 3/4 power of mass over 27 orders of magnitude. And this is what I said a moment ago. But that has an interesting implication, which I just referred to, and that is the metabolic rate per unit mass of tissue or per cell decreases with size. So even though the same cell in a different environment is operating, its time scales are somehow determined by the environment in which it is, even though it's the same liver cell, to all intents and purposes, in a whale and a shrew, the whale is incredibly downregulated in terms of the rate at which it works. Similarly, here's something much more mundane than that, heart rate. We have this, here's your heart rate, and it also has the same 1/4 power, as you can see there. The slope of it is very close to minus 0.25. And it's the same thing. Somehow, we are down-regulated relative to our dogs and cats, but the elephant is even more so in terms of the macroscopic physiology of our body. And as I say up here, and I will emphasize later, metabolism, of course, sets the pace of life, and small animals necessarily live faster than large ones because they are governed by this scaling law. So there's no theory here. This is just the data. This is just expressing what the data is. So I want to just go tangential a moment just to show you the ubiquity of these scaling laws, but these are spatial ones. This is the radius of your aorta versus size, and it's got it's very good scaling, and the slope is 3/8, which means the cross-section, the square of this, goes as 3/4. But also, it's the same as tree trunks. Your aorta scales the same way as tree trunks. That's the length. Length goes, again, with the scaling as the exponent, the best fit, very close to 1/4. This is over 21 orders of magnitude for plants. Here's U. This is what you think of as you. This is your brain, your white matter to gray matter in the brain. And you can see, again, an extraordinary scaling law. And this one scales like the 5/4 of mass. So to all intents and purposes, at this coarse-grained level, we're just scaled versions of each other, despite appearances. Here's even genome length versus cellular size, much more variance here, much more, so to speak, noise. And again, the slope is about 1/4. And what you see emerging here are these extraordinarily regular, unbelievably simple scaling laws underlying the extraordinary complexity of living things. And they're dominated by this number 1/4. That's called quarter power scaling or allometric scaling. It was first discovered 70-odd years ago by a man named Max Kleiber. So this is one I just referred to earlier. Lifespan, it turns out, there's lots of variance in the data. Somehow I missed the slide here, but it doesn't matter. There's lots of variance, but here's the point. Increases with a quarter power, whereas heart rate, I just said the time decreases as mass to the 1/4, which means if you multiply them together, we have something that is an invariant. The increase of 1/4 is cancelled by the decrease of minus 1/4 in heart rate. So heart rate times lifespan is an invariant. It's the same for everyone, but lifetime times heart rate is, of course, the number of heartbeats in a lifetime. So there it is. So going to what was said earlier, there's this beating, roughly 1.5 billion beats, and that's it. And that's across all mammals. And I will come to human beings, if I have time and remember, near the end. That's sort of extraordinary, and it's almost, at a coarse-grained level, taking us back to Newton, that there's this somehow this amazing metronome that's sitting there in some cyberspace controlling lifespans of mammals in particular. So, of course, this begs the question, where in the hell does all this come from? I mean, what is it that's leading to all these? And that's, of course, a whole other lecture of itself. And the idea is that it is the generic, universal properties of networks, the mathematical and physical properties of networks that are underlying this, and their fractal-like nature. And I wrote here, I'm not going to spend time on it, just 3 generic principles that underlie pretty much everything I've shown you, and 50 other scaling laws I could show you, all with this 1/4. You can read them. I'm not going to go through it because it's not the focus of this talk, but they're very general things, like the network has to go everywhere, has to feed every part of the system. There's a kind of optimization principle that the network optimizes something such as, for example, the amount of energy needed to keep the organism alive so is minimized so that you can maximize Darwinian fitness. So you minimize the amount of energy your heart has to do to pump blood through your circulatory system so that you can maximize the energy allocated to sex and reproduction, and so on. And I'm not, as I said, I'm not going to belabor that. We are a bunch of networks. Life is a bunch of networks. There you are in the middle there. And down in the left corner is your brain, and on the right, inside your cells, inside your mitochondria. And when you analyze this all mathematically, which as I say, I'm not going to do, you can derive these scaling laws. And you can also derive the structure of these networks. And the answer is given at the top. B is metabolic rate. And what you discover is if you live in D dimensions, you get that the answer should be a scaling law, which is a power law with an exponent of D over D plus 1, where D is the dimensionality you live in. We live in 3 dimensions, so it's 3/4. And you can see that the dimensionality, the 4, the 1/4, is actually a reflection of the fact that we live in 3 dimensions, which gives rise to the possibility of testing it with 2-dimensional plants and so on and so forth. Again, I don't have time to go into that. But the plus 1, comes from in sort of hand-waving way, from the fractal nature of these networks, arising from the fact that these networks are trying to optimize something. Okay. So You can derive all this and derive it all for the network, some for spatial things, some for time scales and so on. And I'm not going to, again, belabor this. You can make predictions, and it agrees. You don't have time to absorb this. It agrees somehow extraordinarily well, too well in some ways, with all the observations. Here's for the respiratory system. Here's for plants and trees. This is for forests. This is a collective, and so on. I just want to get across that one has a theory, a mathematical theory, from which you can predict many, many things, and many things to do with timescales. And I don't have time to use this to show you why it is, in fact, you live of the order of 100 years, or why it is you sleep 8 hours a night. I'm only going to focus on one thing to do with time, and that is growth for the moment. Okay. So here you are growing. And of course, that's a scaling phenomenon in itself. And, you know, the way you work, of course, is you eat, you metabolize, you send metabolic energy through the networks, controlled by all these mathematical laws and so on, and down to cells. At the cellular level, it maintains those cells by repairing damage, replacing ones that have died, and then creating new ones. So there's the equation for it in English. You allocate between maintenance and growth. And here it is in a serious and a little more serious language. And I've stripped all the bells and whistles from this. But roughly speaking, without being, just to keep it very simple, the metabolic rate is proportional between the first term, which is the number of cells that are there, and the metabolic rate that's required of each cell. And then you add cells at the rate dn dt, t being the Newtonian time. We'll come back to this. And E is the amount of energy needed to create a new cell. So that's a very simple equation. And you can rewrite it because you know the number of cells is proportional to the mass. And here it is in terms of the mass. It's a very, very simple equation for the growth of any organism. Not only that, the parameters in that, what I called A and B, are universal parameters. Average mass of a cell, average energy needed to create a cell. So that this equation describes the growth of any organism. It's amazing. And there's the solution to that equation down here. You don't have to compute it. You don't just look at it to see that there is. Now, when you do that, here's an example. That solid line is a prediction from the theory, and that's data points. This is for us as rats. And what you see is just this sigmoidal growth. You grow quickly and then stop. And you can trace back the fact that you stop to the fact that metabolic rate expresses an economy of scale. You had sublinear scaling, 3/4 less than 1, giving rise to an economy of scale. And if you go back to this equation, you can immediately understand why it is that you stopped growing. And that is that, if you look at that equation up there, metabolic rate increases as mass to the 3/4. That's the 3/4 there. Oh, I have a pointer here. They gave me. How do you use one of these?
Yeah, pointing the other way around.
Am I pointing the wrong way? Yeah, I don't know. I'm a theorist. I don't know how to. So metabolic rate, that's the 3/4. This is the number of cells, which is linear mass. So the source of energy is only increasing with the 3/4 power and slower than what it's feeding, the growing of the biomass of your body. So what happens is you outstrip the rate at which you can supply energy. So this eventually goes to 0, dm dt goes to 0, you stop. So it just stops given by the dynamics of the situation. No genes need to be involved or anything. It just happens. It's guaranteed to happen. And so here it is. Here's that same equation applied to a couple of other mammals and a fish and a bird and so forth. And because it's universal, that means that you can use the mathematics to rescale everything so that everybody grows at the same rate. If you look at it through the right lens, all of these complex times and different times actually are the same because there's a universal theory. There is a universal time governing them, and there it is. And you can see it's coarse-grained, as I said. There's some outliers and so forth. And here's just some small sampling of animals, and this is a universal graph. I'm not going to go into the details of how you rescale, but it's given by the theory. And that line, that solid line, there's a mathematical formula for that line. It was taken by some other people, and they did it for not just insects, which we hadn't done, but insect communities, social insect communities, whole beehives or whole ant hills. And that's what you see more outliers, but that's what these are. And you see it's surprisingly good. And then we also had a theory of cancer, and those tumors that sadly sometimes grow in us also satisfy this. Of course, because they're the same thing. They're semi-autonomous organisms, and they just follow the rules, and they grow. And those gray points, all the gray points you can see on this, are tumors. And we were stimulated by this because of this graph, actually. The formula was taken by some oncologists at Harvard for a whole bunch of tumors, and then they actually did it wrong, but that doesn't matter, but the idea was right. And then we concocted it into this universal graph. And many of these points are organisms. On this graph are not just tumors, but organisms. And by the way, you see something, probably everybody knows, that solid tumors, like you, stop growing. Which, by the way, also, if you want to truly speculate, gives rise to the possibility that one way of controlling cancer, of course, is not to try to get rid of it, but to fiddle with the parameters so that they stop growing very quickly and they just sit there and do no harm. Anyway, we've talked about that. So here's the point. The network geometry and dynamics controls the pace of life at all scales and leads to something I just called universal time. It's universal in this sense for these animals. And indeed, the pace of life systematically slows with increasing size, but in a regular, predictive way. So there it is, that all rates, everything from metabolism, growth, the rate at which you evolve, how long you live, diffusion of some oxygen across membranes, fluxes of various, it doesn't matter. Whatever it is, they all obey this same very simple scaling law, all controlled by the same time, okay, the same time. And you can write it in terms of times as well, either way, rates or times, lifespans, time to maturity, and blah, blah, blah. Now, but there's another aspect that changes time. So this is the controlling of energy and its relationship to time. But another form of energy, which we are not so conscious of, well, you're conscious of it if you live in Singapore, is heat, temperature. We and mammals are almost unique in that we keep the same body temperature. Everything else on this planet, everything, changes with the external environment and is very, very sensitive to temperature. In fact, it's very, very sensitive. So I want to just tend to say a minute or two about temperature because it does relate to time. One of the things I took out of this talk, by the way, was the whole question, the classic question of the arrow of time on causality and the role of entropy. But that's sort of buried in here. I will maybe come back to it at the very end. The way I've been talking about metabolic rate here is the flows of energy to support cells or parts of the system. But of course, metabolism comes from chemical reactions that I mentioned earlier in the respiratory complex. And it's a sum of a whole bunch of processes. And one can use classic chemical reaction rate theory. And I won't review that for you. I've just written it down here. But the important thing is there are two major components. One is the fluxes of things, the generic fluxes of things. And that sort of is represented by this 3/4 power. But there's the kinetics, the fact that there's statistical probabilities of chemicals interacting with each other, meeting each other and interacting in a finite time. And that's governed by the famous Boltzmann or Arrhenius factor, exponential of minus e over kt. K is a truly universal constant called Boltzmann's constant, like Planck's constant for quantum mechanics. T is absolute temperature, and E is the so-called activation energy, how much energy to create the reaction. And there's some average number for that, for ATP. And this number is typically, in units I like to use, a little less than electron volt. It's typically around 0.7 electron volts. So go back to this, which I had a moment ago. If we add in temperature, there's a temperature dependence to the rate at which we live. So the rate at which we live is of everything around us, except what goes inside our bodies, is highly sensitive to temperature. And it's exponentially sensitive. And I'm now going to make an editorial comment, because one of the things that upsets me enormously about people who work on global warming is that they seem not to be aware that temperature, that what the effects of the work that they're doing, the reason that it's important, that 2 degrees is important, is because it's exponentially dependent. That's a huge effect when it's exponential. If I tried to tell my mother that it matters if the temperature rises 2 degrees, and she says, well, that's weird because it changed 40 degrees last night. So why should 2 degrees make a difference? So it's because of exponential rates over time have of the effect of temperature. Sorry, that's editorial, nothing to do with this talk. So to put it in simple terms, almost everything around you, in terms of its very low resolution, coarse-grained behavior, all of life around you is determined by just its size, its mass, and the temperature at which it's operating. Usually that's the ambient outside temperature. And so if you take any time and any rate and you take out these factors, it's the same for everyone. There's an invariance. Okay? And it's governed by just 2 numbers. Only 2 numbers dominate coarse-grained behavior. The 1/4, coming from the physics and mathematics of these networks, and this 0.7 electron volts, roughly, related to the chemistry of the production of ATP. And that, of course, at a more fundamental level, those that are physicists, is, of course, determined because it's all electromagnetic. It's quantum electrodynamics, so it has to be of this order. So now, let's see. I'm going to miss, well, I'll say I'm going to miss this out, actually. Oh, no, let me see. So evolutionary rates, for example, you can determine from this. If you assume that, for example, much of the damage, most of the damage that's being caused is being caused by metabolism, then so you can construct a little model, little theory, for the rate at which DNA nucleotide substitution is taking place, and do the calculation. And here what's done, we didn't do it as invariance. That's because biologists, my biology colleagues, don't like to plot things that way. So that's another thing. They like to do it this way. So what is done here is you take the measured quantity of the rate of evolution, the rate at which nucleotides are changing, and you take out the 1/4. Normally I would say then you take out the temperature, but no, they wanted to plot it versus the temperature, which is over here, and versus inverse temperature, actually. And you should get a straight line if you plot it in this way. And indeed, there you get the straight line, and the slope should be roughly this 0.7, which is what it is. Okay, and these are for various things like mitochondrial DNA, cytochrome B, RNA, and so on. And similarly, you can do it the other way around. You can remove the temperature effect and plot it versus mass, and you should get numbers close to 1/4 minus 1/4 for the slope. So it's just verifying it at the evolutionary scale as well as at this more physiological level that I was talking about earlier. And I'm going to miss this, and I will do this last thing, just mention it. because it's kind of amazing, really, when you think about it, that lifespans, how long you live, if you're not like us, is determined by the outside temperature. And here it is here. We've taken out the mass dependence and plotted it versus the inverse temperature. Well, you can see there's a nice exponential rise on the way it's been plotted. And the slope is in agreement with the prediction, and it's for everything from little diddly things like rotifers and so on, all the way to big fish. So so there is this kind of universality of timescales by which biological life lives. So that's just sort of a summary. We have these amazing nonlinear scaling laws. They express an economy of scale. The bigger you are, the less per capita, the less per cell is needed to stay alive. The pace of life systematically slows down following the quarter power law. But that implies that there are invariant timescales, what I whimsically called universal timescales. And in particular, I discussed growth, showing that that was also universal and has this sigmoidal shape, and it reaches a mature, stable state, ultimately. And all of this can be understood via networks. And by the way, what I didn't add to this, and then you die. And that is also given by the networks. And that's given by the dissipation in networks. So I now want to move, as quickly as I can, to discuss taking the same framework and applying it to socioeconomic life. So the first question, and in particular to cities, because cities are, well, I'll explain why in a minute. So the first question is, to what extent is that the same as that, if at all? Well, there are certain things in common, obviously, and we often use much of the language of this to discuss this. You know, we use metabolism and ecology and DNA in all those best-selling books about how to run a business or all the rest. They use all these terms metaphorically. And the question is, does it have any substance? So I want to focus on cities just very briefly to give you a sense of that and talk again about some of these questions of time. So that's a city. That's the object we're now going to look at. And, you know, cities have all these marvelous things that attract people to them. Greater material wealth, job opportunity, a buzzier, sexier life, access to bigger cultural events, fancy restaurants, better education, and so on. But all of that has to be supplied by energy. So there is obviously an analog to metabolic rate of a city. It has a kind of social metabolic rate, which I will come to. And it all has to be supplied by energy. But of course, if you supply energy, and this is where I bring in entropy, if you supply energy and you transform energy from, you know, ultimately from the sun into these buildings and us and roads and all the rest of the stuff, that creates entropy necessarily. Second law of thermodynamics, no way around it. So it produces socioeconomic entropy like this, and this, and this, and this, and this, and this, and so on. All of these things are the result of ultimately, from a physicist's viewpoint, transforming energy and the unintended consequences thereof. So I'd like to show this. This is sort of silly, but that, believe it or not, is a picture taken by a satellite of the night lights in 1940. Well, of course, which is the year I was born. That's why I chose 1940. Of course, there weren't satellites. If we had the lights off, you would actually see something here. You see faint lights. I've done the calculation. This is what it would look like. With the lights on, you can't see it. But even with all the lights blaring, in the short period I have been on this planet, it has gone from this. It's beautiful here, actually. I can see the pictures. It's gone from that to burning up. Absolutely bonkers. You know, it's gone completely crazy, right? And what does that represent? That's just all cities. That's all urbanization. And that's you. That's us here now. at night, last night. Well, it wasn't taken last night, but last night. So this has happened at an exponential rate, and people that say, you know, oh, the fourth revolution is going to be exponential, have not recognized that it's been exponential for at least 200 years and probably much longer. That's the way it is. It's not new. We live in an exponentially expanding socioeconomic universe as well as an exponentially expanding universe. Actually, we don't live in an exponentially expanding social universe. We live in a faster than exponentially expanding. So here is just some simple numbers. The United States went from a few percent urbanized to over 80 in 1800 to over 80% now. It's about 82, 83% now. The world crossed the halfway mark just a few years ago, and it's headed for that 80% level somewhere towards the second half of in the second half of this century. And again, just to give you a scale, so that, my God, talk about time scales, that is what we're living in. That is the background that we're living in right now, this like, unbelievable expansion, like a balloon going like this. So here's what it's equivalent to. It's like adding about 1.4 million people a week, urban, if you just do the average. I mean, it's crude, but anyway. And that's like adding a New York metropolitan area every couple of months, 15 million people, or all of this around you, all of Singapore every month. That's what we're doing now, okay? So that's extraordinary, and of course it's a reflection of this. There you are. You can see it's faster than exponential just looking at it. That's the population growth, and it's gone from a couple million, 2.4 million when I was born, to over nearly getting on for 8 billion now, just in my diddly little lifetime, which is unbelievable. And it of course, it was expanding continuously from when we started speaking to one another 10,000 years ago. And the great discovery, of course, was the Industrial Revolution, when we did the two great discoveries, the discovery of fossil fuel and the discovery of capitalism and entrepreneurship. And that changed everything. And that made us going from a very slow rise, very slow exponential, to something that's super exponential. And of course, the fundamental question is, that's just the US GDP from 18, just to show, I'm going to miss that. So everything is exponential. Everything just keeps going. It's just, that's the way it's been. And the big question is any of this actually sustainable? Or is it, it's the old Malthusian argument, which I will come to later, which was wrong, by the way, but I will come back to it. So here's another example. China, slow to urbanize, crossed the halfway mark just a few years ago, but is headed towards this 80% level. It claims to be building, actually it has to build in some sense, 200 to 300 new cities in the next 20, 25 years, each in excess of 1 million people. Well, that's going to happen, and that's a huge time scale. I mean, an enormously short time scale, of course, but a huge effect. Everybody on this planet is going to be affected by this, and that's just China. We have India and Africa and parts of Latin America and so on. So the whole question of whether this is sustainable clearly lies in the fate of our cities. What is that if we don't understand our cities, then as far as I'm concerned, it doesn't matter how much work you do on climate change or understanding financial risk or anything else, unless you understand the dynamic that produced this and is continuing to produce this, you will never come to terms with it, and the best we could do is to mitigate some of the problems as we go along and muddle along. But so I felt just a couple of years ago that one should try to think about developing a so-called science of cities, which may be an impossible task, but it's something that one should at least start thinking about. So on the one hand, all the problems that we face and the huge global challenges and local challenges we face come about because of urbanization and the role of cities, but they're also the solution, and it's that dynamic that is the crucial one. They're also the solution. Why? Because one of the major characteristics of cities is that's where all the smart people are. They attract all the smart people, and all the great ideas and all the great wealth is created in cities. So that's what I said. We urgently need to ask whether there's a quantitative science of cities involving, just grandiose terms like this. Now, again, as in biology, you can't have a physics of cities in the sense I described. There can't be precise laws and precise, predictions. That's crazy. But again, maybe we can do the kinds of things we did in biology, understand in a very coarse-grained sense some of the dynamics, and in a quantitative way make predictions and so on. And maybe in that sense we can understand some of the dynamic that's going to come in the near future, as well as understand and mitigate or minimize unintended consequences. Now, the way, of course, we deal with them, the typical way we've been dealing with all these problems, which has been extraordinarily successful, is that we put things in boxes. And this is just something arbitrary I did. But we tend to deal with all of these things as if they're their own thing. So we think about education, we think about transport, we think about health, we think about the finance, and so on. And they basically they hardly interact with each other, whether it's practitioners, policymakers, or academics. I just drew it like this, but each one of these, there's a box around inside each of these. I mean, there's boxes within boxes, and everything is highly siloed. And one of the things that we have learned in dealing with complex adaptive systems is that is a very dangerous thing to do. We need to think in much more integrated terms, and to not only recognize that each one of these is a complex adaptive system, but that they are interrelated with each other, and the whole thing is itself a complex adaptive system of complex adaptive systems. Yeah, so that's what I said there. So here is an attempt at just scratching the surface of trying to approach this problem, and it's using the framework and paradigm I just talked about in biology. So the first question is, are cities scaled versions of one another like organisms are? A whale, an elephant, a giraffe, and a person look quite different, and they have very different environments. But one of the things that we just discovered is at the kind of this coarse-grained 80-90% level, we are in fact scaled versions of one another in terms of anything that you can measure about us. So is that true of New York, Los Angeles, Chicago, Santa Fe, for example? Are they scaled versions of one another despite having different histories, geographies, and cultures? Well, two things. One major thing might, if you believe what I told you earlier, may give some hope that there might be something to it, is, of course, you recognize that cities are, to a large extent, networks. They're physical networks, infrastructural networks of various kinds, there's Singapore, transporting people and resources and energy and so forth, and they're supplied by networks. And this is what everybody focuses on, or mostly focuses on. That's when you think of city, you focus on the idea of the roads and the transport and the buildings and so on. That's your image. You think of Paris, you mostly think of, the boulevards and the Eiffel Tower and so on. You don't think of the things I'm going to talk about in a moment, and that is the people. Shakespeare, of course, who understood everything, as far as I can tell, understood that, indeed, this aspect of the city is the infrastructure, and what I have termed the hegemony of the infrastructure is, in fact, in some ways, the least interesting part of the city. The really interesting part is the way people interact with each other, because the city is a platform, a stage, a theater for facilitating that interaction. That's how it evolved, and that's how we invented it. It may be the most crucial, important, and outstanding discovery human beings made, was to invent this machine to do what we're doing here, bring us together to interact and create ideas, innovate, create wealth, improve quality and standard of living, and so on. So here's a network, and many of you will recognize this. The nodes, of course, are people, and the lines are those that they're connected to. And many of my colleagues, this is the way they think of them, and they look at data related to this, and they derive little theorems about it, and that's very good, except it's missing, in particular, one crucial aspect, and that's represented by things like this, namely, it is indeed people interacting, but they're interacting also with the infrastructure. You have to have that backdrop. You have to have this. This is Orchard Street, down the road here somewhere. People interacting. And this, which is even better, and this is another timescale issue. So here are people gathering, and symbolically, people have been interacting with each other, exchanging information, creating ideas, innovating, as they're doing there, at the same stage for over 2,000 years. Those people have been doing things like this. They're all dead and gone. But the same structure is there with this resilience, which is providing this framework for interaction, creating ideas. As here, too, this is New York 120 years ago. Those buildings are exactly as they were then. All those people are dead and gone. Almost no one behaves like this anymore. But what is going on there, symbolically, is still going on in New York. And New York is the greatest place on the planet for this, bringing people together. Now they're mostly inside buildings. Again, creating ideas, wealth, innovating, and so on. Now, mostly, of course, this situation, almost all the ideas being created are useless and pointless. I mean, when we meet and talk, it's all ephemeral and so on. But here's the magic. Here's the magic. The magic is that if you keep on doing this, you eventually produce a theory of relativity, or you invent a Google or an Amazon. It all came from there. I mean, symbolically. Obviously, and maybe they even did this. I don't know. But that's symbolically what cities are for, to provide that environment. So the thing that is missing from my colleagues' wonderful analyses of this is that each one of those nodes is in a place like that. It's grounded somewhere. It has everybody, and it doesn't matter, everything may take place in cyberspace. Every person has to be on a two-dimensional surface, whether they like it or not, somewhere. But even more than that, it's not just somewhere. This is also misleading. They also have to be moving. I mean, they may not be moving all the time, but you have to move. You have to go from your house to NTU, or take someone to school, or go to the theater or the store. There's movement. So what you learn from this is that that social network is actually integrated in a very powerful way with the infrastructural network. And if you only look at one and not the other, either way around, you are missing some fundamental aspect of the entire dynamic, which has brought us to this. The other thing about this is that we also have modular structure. We have families and groups and divisions and so forth, and that also has a regular structure, which I don't have time to go into. But so I'm going to turn immediately to the question of scaling. Do these cities scale? So here's a piece of infrastructure. This is number of petrol stations versus city size in 4 European countries. And you can see it scales like biology. It's a little more fluctuations. But, and you can see that it's sublinear. The dotted line is linear. The bigger you are as a city, the less gas stations you need per capita. And the slopes of all these hover around 0.85. You save about 15% every time you double the size of a city in terms of gas stations. So here's the amazing thing. This is true. This little law is true for every urban system across the globe that we have found data for. Gas stations. But even more amazing, it's true for all infrastructure. If you look at the length of the roads, the length of the electrical lines, the water lines, anything. Anything where you can make measurements of infrastructure, it always has this same characteristic. that you have this 15% economy of scale in the infrastructure. Well, that's sort of the dull part of a city. It's the biological part. Here's the interesting part, because this didn't exist before we stopped being hunter-gatherers and formed sedentary communities and started talking to one another and starting this process of sitting around and talking and exchanging ideas and disagreeing and agreeing with each other and so on. When we did that, we created things like wages, and we recognized that there are some people that are smarter. I'd hate to say this in the days of inequality. Some people are more successful and smarter than others, and this man in Richard, Florida, is called the super creative, professional people like you. And if you plot those versus size, you can see scaling. There's more good evidence of scaling, more fluctuations. But the new thing that happens is the slope of these, instead of being less than 1, is bigger than 1. In other words, instead of the bigger you are, the less per capita, it's now the bigger you are, the more per capita. You have 15% more wages, 15% more professional people, 15% more patents, 15% more ideas being produced, the bigger the city, when you double. 50% more crime, also a very innovative phenomenon. 15% more police, tax, and so on. 15% more fancy restaurants. Anywhere in the world, doesn't matter. Whatever socioeconomic quantity you look at, and here it is. And some of these are timed, like patents. That's patents produced per unit time, the rate at which you produce them. So there it is, and I just put a panel of 6 metrics in 6 different countries. And you can see just by eye, they're pretty much the same in terms of their slopes. So in English, what that says is the good and the bad and the ugly come together. On average, when you double the size of a city, you systematically increase income, wealth, patents, colleges, and all these other things, the good, but also the bad, the disease and crime and so on. You increase all those by about 15%, and at the same time, you save approximately 15% on all infrastructure. So cities are good in the sense that they produce all this, and the bigger they are in this sense, the better. Better to be big if that's what you want. And of course, this is also, you could speculate, this is of course the reason they keep growing, is that people are very good at repressing the bad stuff and get attracted by getting more money, more power, more education, access to more cultural events, and so on and so forth, more social interactions, and they're attracted to that. So each person at an individual level is attracted, but collectively we say 15%. And the question is, where does that come from? And I, again, don't have time. I just have to tell you, it comes from the mathematics and physics of social networks. It's the dynamics of those social networks that leads to this. And I just tell you in English what it is. It's that I talk to Steve, he talks to Peter Ho if he wakes up. Peter talks to me, I talk to Guan Ying, Ms. Novotny, whom I recognize now, and talk back to me. And we have this conversation, and ideas develop, and you realize it's a positive feedback mechanism. We keep adding. That's the nature of the beast. And by adding, we also speed up time. So that's where I had to do all this to show you how this leads to the speeding up of time. And I just want to do one thing on that briefly first, before that, because this is a theory, and in theory we test. I sort of gave some implicitly tests of the theory. I showed you those tables, but I want to give a test of the theory here. So here's just putting together income, GDP, crime, and patents, 4 very different things on the same graph. This happens to be the United States. And if the theory says it is the interaction coming from social networks that is underlying this, therefore, if you can measure the rate at which people interact as a function of city size, it should track that. That's the idea. It should be the same. If that generates, if it's interactions and the rate at which people interact that is generating higher GDP, more crime, more ideas, greater income, if that's what you're doing, then if you could measure that it should be the same. So this was a collaboration with some folks at MIT. And the way you do it is, I don't have it with me, my cell phone. Everybody carries a cell phone. I'm sure you're very familiar with this. Everybody carries a mobile phone, which means that everybody, the motion and everything you do, of course, is known. I mean, everybody, you're being this little detector. So it's like having a detector on every molecule in this room, knowing exactly where it is, how fast it's moving, which is sort of useless knowledge. But for us, it's incredibly useful. So the phone companies and Google and so on are very powerful in that they know this. So it turned out we were able to get hold of billions and billions of these damn phone calls for various places and analyze it in terms of deconstructing it into where people are in cities, and ask various questions, one of which was the one I just asked. How often are people interacting between each other as a function of where they are? So I call Steve, and within 6 months you call me back. That's we define we have a relationship. Could have made it 3 months or a year, it doesn't matter, there's some threshold anyway. And we did that for the United Kingdom and Portugal, and there's the data on the right, plotted in the same way, and you can just see it's basically the same slope. I think the blue is the United Kingdom, and the greenish one is Portugal. And you see they lie on top of one another with the same slope. So you interact more and more, faster and faster, the bigger you are. I will miss this out, and I think I've probably gone way too long. I probably better miss this out. This is actually to do with time. I'll just say it. This is about the movement in cities. Movement is related to time, and most people, when they move in a city, are going to some place and coming back, and they try to do it in the shortest time by the shortest possible route. So if you take that and use some of these ideas, you can determine you can derive a remarkably simple law for how many people are coming to a given pixel inside a city from a distance r away, f times a week. How many people are coming to the area, well, I don't know, some area around here. Not the university is a bad example, probably. From a distance 5 kilometers away, twice a week. How many are coming from 10 kilometers once every 6 months? That's the formula. So here was data for Boston, Dakar, Senegal, Lisbon, and Singapore. And you can see they all lie on one another, and that dotted line is that prediction from the theory, and it's plotted, as you see, versus R times F, which is what the theory said. But this is Boston. I'm going to miss that. This is Singapore. This is taking various areas in Singapore and asking exactly that question, those lines. Those are the data from analyzing these cell phones calls, and the blue line is the prediction of the theory, the inverse square, which means that you could determine how many people are coming to your little area by this formula. It's amazing, but it's time. So, okay, move on. I want to finish off quickly with a couple things. I sort of indicated before the network dynamics determines the pace of life. It's basically determined by the metabolic rate. If the metabolic rate is sublinear, economy of scale, we saw in biology, the pace of life slows down the bigger you are. Here, the slope is superlinear, coming from this positive feedback, and that leads to the pace of life systematically and predictably speeding up. So all the things we talked about earlier could be understood within this theory. And here's the example. On the left, I showed you heart rates. Here is a whimsical graph. It's the speed of walking in cities. It was data taken about 40 years ago, funnily enough. We found in the literature the speed of walking in European cities, and the prediction agreed very well with the theory, despite there's quite a lot of fluctuations. And just to give you another sense of time, Here's something I saw in a British newspaper about a year ago, and I'll read the caption. Research revealed almost half the nation, that is the United Kingdom, found the slow pace of high streets to be their biggest shopping bugbear, meaning half of the people wouldn't shop downtown because they found too many people walking too slowly. It's about the pace of life. So this picture is the first day in the city of Liverpool where they initiated a fast lane for walking to avoid this problem. So here's sort of really on the ground version of this problem of the pace of life. I'll finish up with this growth equation. It's the same thing as before. You have a social metabolic rate, which is it's buried in here of many conceptual questions as to defining the social metabolic rate, but we have to assume that we can understand that. The social metabolic rate, and what happens, you add all these things together, that has to be allocated between maintenance and growth. You maintain all the people that are in the city, and you maintain all the buildings and roads, you repair them, repair the people with doctors and hospitals, and the roads with machinery and so on, and then you grow new people and new buildings and so on. So you can put all that into some humongous equation, and amazingly, when you use the theory, you boil it all down, you get a very simple equation that looks like just like the biological one. Okay. So there it is there. It's very similar. The only difference is that in the I left beta. Beta was 3/4, except it was mass instead of number of people, 3/4, and in cities and in socioeconomic situation, it's 1.15. Okay. So when it was 3/4, we saw it gave rise to this, stopped and so on. That'd be terrible in our paradigm, present paradigm, because everything stops. We're supposed to keep growing forever, so that's not good. And indeed, the theory is wonderfully consistent, because if you put beta equal to 1.15, you immediately see everything I said. It's a feedback mechanism. The thing is open-ended growth, because n to the beta, n to the 1.15, always beats n to the linear n. So dn dt, every time you is getting faster and faster and faster. It's just like us interacting, our little group interacting, we generate. So that's it in the equations. And there's the solution in hieroglyphics. And symbolically, here's what happens. So instead of getting that sigmoidal curve, you get a super exponential unbounded growth. Wonderful. So it's very wonderful, and it agrees with data. I'm sorry, I'm going on way too long. I will finish very shortly. And that's great, except those that are mathematically inclined would recognize that this equation, a so-called logistic equation, has built into it a fatal flaw, so to speak. Not the flaw in the mathematics, but a fatal consequence. And that is called a finite time singularity. And a finite time singularity is, and this is where, this is the mathematics underlying all the bullshit of Kurzweil and so on. This is the origin of singularity. And that's represented by that dotted line. This thing goes up. And the trouble is, this, whatever it is you're measuring here or sensing, has to become infinite, which is obviously crazy, in some finite time. So it could go infinite in 5 years, 10 years, 100 years, but necessarily it becomes infinite in a finite time, not like an exponential. This is very important to recognize. An exponential goes infinite in an infinite time. So that doesn't matter. Who cares about what happens in infinity? But you sure as hell care in some finite time. And the theory tells you what happens is as you approach the singularity, you stagnate and then collapse. So that's the trajectory that is on, if you believe these equations and the analysis, which, by the way, is, as I said, in very good agreement with the data. So how do you avoid that? How have we avoided it? Well, you'll recognize it. First is to recognize, this is just redrawing it here, is to recognize that as time increases, we are assuming, so to speak, that roughly speaking, the background that we're in doesn't change very much. You know, we've discovered iron, whenever that was. When was it? I don't know, 10,000 years or I don't know, whatever. We discovered iron, and that sets a certain paradigm. We discover coal, that changes things, and so on. We invent computers, then we invent IT. Each one of these is a major paradigm shift, or I like to think of it as a resetting of the clock. So as you're going along here and hit the singularity and would collapse, you better have a major paradigm shift, a major innovation, and you can start over again. And of course, you repeat the pattern. So there's a kind of theorem, which won't surprise you, and that is, in order to sustain open-ended growth, you must have continuous cycles of innovation, which is what people often say. Economists have known, and so forth. However, this is a theory with equations, and equations tell you what happens. It has another fatal consequence, and that is, not only as you go along each one of these curves is life getting faster, life is speeding up, but the time between the innovations gets shorter. So socioeconomic time is continually contracting in the sense that life is going faster and faster to do the same kinds of things. So that's a huge question. If you take that argument to absurdum, obviously this is not sustainable. The last major innovation took maybe 20 years. The next one will take maybe will take less than 20. And eventually, if you took this argument forward, eventually you are going to have the equivalent of an IT revolution every year, every 6 months. Completely nuts, obviously. So this is not sustainable. So I just want to show you some data. I have no idea who this guy is. I'll try to find out. I saw this on the web, so I don't know if but it was interesting because it looked like what I just showed you. But what he did was, this is time to reach 10 million customers, telephone, cable, and so on. And he just said some numbers, just to illustrate. This is some sort of proxy for the pace of life speeding up. I show it because, A, it looks like what I just showed you. But if you take these numbers, they fit exactly the prediction. But more importantly, we did an examination, just going back to cities specifically for the moment. We did an analysis of New York from 1790 to the beginning of this century. And I'm not going to go into detail, but what we did is we looked at the fluctuations around sort of a smooth growth to show that the fluctuations around that growth get tighter and tighter. The oscillations start to pile up. So it was, again, and it agreed, again, the data agreed, and that's what little panel up there agreed with the predictions. And here's this is data from the infamous Kurzweil, who caught on to this idea of singularity and thinks that the next singularity, of course, is going to be some glorious cyborg, I don't know what, anyway, something. I see things somewhat differently, but he did create some data, and this is not mine. So what's plotted here is how long it took for one of these things to develop. So it took 1 billion years for cells to develop over 1 billion years ago. And here it took, just 10 years ago, it took 10 years to create the internet, and it happened about 10 years ago, or 20 years ago. That's it. It's on the same graph, it's plotted logarithmically. The reason I show it, I should say I don't actually believe this should be on the plot, but I just copied what he did. That line is the prediction from this theory, that line of the rate at which you have to innovate in order to stave off. And just again to show you the increasing, that's logarithmic, which of course distorts everything. But here it's plotted where it's linear in time, and it's the same thing, and what you see is that everything piles up now. Everything piles up now. All these things pile up now. Everything is happening at once, and so on. And the question is any of that sustainable? And I will leave you with that. I have my own thoughts on that, of course, but I'll leave you with that conundrum. Of course, it's speculative. There is a theory, just to remind you. The theory is based originally on data, a huge amount of data, in fact. And the theory not only explains that data, it makes new predictions. And if you just extrapolate that theory, then you run into this. In other words, if you do business as usual, it's hard to see how this system can remain sustainable. So I'll finish there, and I apologize for going on too long. And that is my answer to my final question: is there an end to socioeconomic time? And the answer is, if it goes on just as it was, I don't mean, but just the same dynamic. And by the way, just to make it really hammer it home, remember this theory, the results are based on the dynamics of social interaction, how we interact with each other, the structure of our social networks. So what has to change is clearly something to do with our social networks. So if nothing changes, everything stays the same in terms of our dynamic. Doesn't matter how many innovations you make, all you are doing is postponing the problem, and the answer to the question, is there an end to socioeconomic time, would be yes, there is. And I'll finish on that dour note. Oh, can I do one other thing? I'm so sorry. I did want to do one thing because it's very unfair. I want to do two. I'm sorry. I did want to show two things quickly. First, I didn't say that your metabolic rate, this is very important because it links the two times, your metabolic rate as an organism, meaning 20 generations ago when you were hunting and gathering 10,000 years ago, is a little less than 100 watts. Light bulb, that's all you operate as. Now, so everybody sitting in this room is operating, if you add up how much energy you need to stay alive and this kind of life that we lead, it's about 11,000 watts. It's about 100 times more than you should have if you were in synchrony with the rest of life on this planet. And that's equivalent to each person is about a 30,000 kilogram gorilla. Because you could turn the argument around and say, how big an animal operates at 11,000 watts? It's actually about 70% of a blue whale, each person. That's each person, and there's 7.5 billion of us, and even though most of them don't operate at 11,000 watts, they operate usually about 6,000, 7,000. Everybody on this planet wants to operate at 11,000 watts. I just take that as an obvious observation of cultures I've been in, or each one of us is about a dozen elephants. And finally, these are all the wonderful people that did actually all the work. Fantastic group of people whom I love dearly, all associated in one way or another with the Santa Fe Institute. I love them dearly. Here's the lot that did all the work on the cities and socioeconomic. I don't love them as dearly, frankly. They were very good. It was good fun. And here, just to show you how much I love my colleagues, here we are at Jim Brown's either 65th or 70th birthday. See how happy we are? Even though it's so dour, this stuff. And those are the people that gave money for all this. Okay, sorry about that, but oh, no, I'm going to do something really awful, shameless. This is shameless advertising. Look at this. Horrible. Okay. Thank you. Sorry.
Thank you for the wonderful talk, and I think we have time for a couple of questions. So, are there any questions there? Yes, please.
You have several times focused on metabolic rate. Why not a different point of view, not different framework using, for example, information processing, yes, or entropy production, or irreversible processes at all? Why metabolic rate should be so energy? Why it is the central point from this studies?
Well, two reasons. First of all, I left out a little bit about the information theory, which I didn't discuss. I had a whole bit that I took out about entropy, and it's just what you said. Wasn't going to go into it very deeply. But the reason is that there's these amazing scaling laws that are all to do with energy. And energy is the quantity of physics. So it's very natural to start using a physical theory based on energy. The thing that is implicit in your question, which I would translate, is it's extraordinary that just from this point of view, you can understand so much, actually. I find that very interesting that the information part plays a subdominant role. Now, in biology, in cities, also energy plays a dominant role, but you expect information to play a much more important role. And indeed, those are many of the socioeconomic quantities, and indeed, that's where I started to get much more interest. That's why the slides I took out were actually to do with that, not in biology, but in the socioeconomic aspect. So it's a huge area, an open question. Don't know the answer to where it's going to go.
So this has to do with the kind of increasing lifespan over the past couple centuries.
Yes.
So I presume that that's due to kind of externalities that rather than the metabolic rate. Is that basically true?
Yes. So if you ask, as you point out, I mean, if you ask what was the expected lifespan of a human being on this planet in about 1820, it's about 35, between 30 and 35. Now, that includes a lot of infant mortality, and even if you take it out, it's less than 40. And in the United Kingdom, it was, at about 1820, was that number, and it gradually rose throughout the 19th century, so that, this happens to be the numbers I remember. In 1914, the year my father was born, it was 60. And the year I was born, 1940, it had risen to almost late 60s. So I've outstripped, actually, the expected lifespan from when I was born. But you ask yourself the very question you brought up, why? Why did that happen? Primarily, when you deconstruct all the pieces that contribute, the biggest increase is that for the first time in human history, people washed themselves. People learned hygiene. I mean, there was no, there were certain, maybe some aristocrats and so on, but most people didn't wash and clean. And so the introduction of the accessibility to water for cleaning was a big thing. And then, of course, the introduction of sewage and then running water was, and then all the medical things came on top of that.
But continuing that, I was talking with a young person the other day, and this has to do with the rate at which you withdraw your retirement accounts.
Yeah.
And he was saying, I'm planning for 120 to 140 in terms of withdrawing his. So if that's the kind of thing we can continue, what...
So, okay. Because this is a lecture of itself, needless to say. So here's something interesting. If you look at survivability curves for human beings, beginning with ones that some anthropologists concoct from prehistoric times, all the way through Roman times, up through medieval. And what happens is, let's see, your way. In ancient times, it was sort of like this. It was almost exponential decay, and then gradually it started this shoulder, and that shoulder moved out further and further, saying that the mean lifespan was increasing. Here's what's interesting about that. So what you see is this shoulder, this shelf, moving out, except eventually, of course, it drops off. And all of the curves drop off and stop at the same point, which is about 120. And the person, there's one documented person that has lived beyond 120, and that's this lady called Jeanne Clément, who reached just under 123. But otherwise, no one, as far as we know, has lived that long. And if I had put in, which I actually thought of doing, was a theory of aging in this instead of growth, I would have shown you why that is so, why it is. And it's to do with, it doesn't mean to say you can't change it ultimately, but it's to do with all of the parameters that control, in fact, our metabolism. We roughly speaking, you know, the very system that keeps us alive, our metabolism, is slowly killing us because it produces deleterious effects, wear and tear, so to speak. And you can calculate that because you have a theory. You have a theory of these. You can calculate that, and that's how you understand both why mice don't live very long and human beings live much longer, and what you have to do to change that. And the only way to change it is to change some fundamental parameters. And that brings up the huge question that if you start diddling with those parameters, what unintended consequences do you have? So it may be that you can live to 140, but you're confined to lying on the couch all day. You know, I mean, I don't know. It's a very, I think it's a very dangerous game to be playing. And by the way, here's something interesting in terms of time. If you talk to any of the major leaders of Silicon Valley, all the ones that were mentioned, you know, Larry Brin and Larry Page, and all these young guys, maybe not surprisingly, they want to live forever. And they want their company to live forever. And they believe they will. And so they are putting a lot of money into into aging research. But aging research in terms of finding some elixir of life. Peter Thiel is maybe the biggest in some ways. Puts huge amounts in. And I've spent time with these people, and I tell them it's fruitless. That's why they don't invite me anymore. Just the same, I'll probably never invite you back to Singapore when I tell you the whole everything is doomed.
Okay, let's take one more question here.
I don't believe that, by the way. I just...
Professor West, I used to TA for Peter Thiel in Beijing. So can I ask you about your assertion, why do cities keep growing and companies die?
Yes, I didn't, of course, this talk was infinitely long, and I didn't get to why all companies, I have a whole bunch of slides, of course, on why companies die, and showing you the data that all companies die.
Of course, this is a tiny fraction of exceptions I'm talking about. So the first part of your statement, if you look at the ancient capitals of China, except for maybe Hangzhou and Xi'an, the other 6 are kind of small, they're not really growing.
Yeah.
If you're talking about companies that died, and you know, there's a hotel in Japan that's been there since 700 AD, and lots of other companies have been there for 100 years. You have the Catholic and Orthodox churches, if you're talking about collectives more broadly. And then, you know, even for Western corporations like GE, like from Thomas Edison to Jack Welch, at least it lasted for about 100 years.
Yeah.
And then it stopped growing. But Mitsubishi, OCBC, Disney, Berkshire, all of them seem to be growing. Of course, this is just a tiny fraction, and scale and longevity are different issues, but I hope you can comment on this.
Yeah, everything you said is correct. So first thing I would do is say read chapter whatever it is in my book, because it discusses all of the things you just mentioned, in particular that hotel and others. And just to counter that slightly, the oldest company in the world used to be quoted as, I'm afraid my Alzheimer's is at work, I forget its name, a Japanese company that predates those hotels and inns. It was a company that was founded in 585 AD. And here's what's interesting about that company. 2 years ago, maybe 3 years ago, it died. Can you believe that? It's sad. It died, it disappeared. So here's the homework question. What the hell did that company do? What did it make? It wasn't an inn. I mean, so just a side comment first. What you notice about all the companies, the ancient ones, they're in incredibly small niche markets, a special inn, special brewery, and so on. A few of those that are very old. And they're very few. There's a list that it's very small. But this company did actually do something. I mean, as distinct from running it in or making it. Any idea, anyone? It's interesting. It's Japanese. Any idea what it did? Huh?
Fish.
No. See, I'll tell you, there's no point. It built monasteries. Now, here's the thing. Building monasteries in Japan was probably very lucrative from 585 until 1945. And then something happened, and something changed after the Second World War. And Japanese culture made a dramatic change. And people were no longer building monasteries, or very few. And this company was extremely slow to adapt. And of course, this is a famous illustration of the whole point of diversity. If you don't have diversity in your product space, and all you bloody well do is build this one very small sector, you're in trouble. They did get actually taken over eventually by a big construction company to just sort of to keep it. But it died as an entity. So now, these other companies, yes, so if you look at the, I won't show you the pictures, but if you look, we took data of all US publicly traded companies from 1950 until, I think, 2013. That consists of 30,000 companies. That's every company that's ever gone onto the stock exchange. So these are companies that have already been through gestation. They've been successful enough to be floated, and so on. And you then ask, what is the average lifespan? What's the half-life, actually, is the way we expressed it. How long do they expect to live? That number is 10 years. So a US publicly traded company will only last 10 years. From that, you can do a whole bunch of kind of longevity analysis that people have developed in other fields. And indeed, there are a few companies that are serious outliers to that, but they're a very small number that are. And there are almost no major manufacturing companies more than about 100 years old, 120 years old. They all go. GE is not that. GE goes to late 19th century, beginning of the...
Thomas Edison founded
the word, sorry.
Thomas Edison founded the first version in 1878, and then it got merged in 1991.
Yeah.
1891.
So, by the way, I have to clarify something that's very important. Death here means something different than death in biology. In the literature, what it means is the company disappears. So, obviously disappears if it goes bankrupt or is liquidated, but it disappears also if it's bought out. It mergers and acquisitions, and it loses its name and identity. That's the conventional definition. So we use the conventional definition. And by the way, we've done a big analysis of all these companies, and they look very much like biology, instead of having open-ended growth. Can I show you one graph, because it's sort of startling, actually. I'll show you one that is, so that is all of these companies. There's 30,000 companies on this graph, from 1950 to 2010. And what you see, characteristically, is all these hockey stick things happening here. All these upstarts, Google and Yahoo, they're all among these. And then these old ancient ones, like GE and Boeing and so on. Here's when you renormalize everybody to the GDP. It's dead flat, of course. No one beats the GDP. They just sit on there. So they grow very quickly, extraordinarily fast, time scales. Then they age, and then they sit on top of the market. That line is, just to show, is Boeing Aircraft Company. So if the externalities make a significant change, and you are only building monasteries, even though you may be sitting on the top there for 1,500 years, you go down. The great thing about cities is that cities are extraordinarily diverse, and I didn't show you data here of the diversity of cities. Cities go exactly the opposite way. Companies start, they often are diverse, and then they narrow because of market forces. Their product space narrows from possibly many things to a few products that they become known by, and that can persist for a long time. But cities go the other way. Their dimensionality is continually opening. And they do it actually, and again, I didn't show you any of this, in a systematic way and even predictable way in terms of the distribution of different kinds of capabilities and different kinds of jobs and employment. And so in the United States, the most diverse city is, of course, New York, by far, in terms of economic metrics. And so it has all kinds of weird businesses and so on that no other city has. So, you know, so as the market forces changes, it might go into a small recession, but it can bounce back quite strongly, whereas a Pan Am or TWA or Lehman Brothers is very vulnerable. And a GE or an IBM, of course, which basically died, was able to eventually reinvent itself as something completely different. And GE, of course, was able to do that before it went bad. So some of these companies have had prescient leadership that has been able to make that change. But cities do it almost automatically. It's part of the organic nature of a city, whereas I would even say it's part of the organic nature of a company to die. Because the market forces are generally try to force you to be quite constrained and to minimize your diversity. So it's a unique company that's able to circumvent that dynamic. And you know, you cited cases that have been able to do that.
Okay, thank you very much. I think we have to pause here and continue the discussion over the coffee break that is served already. Let us thank Geoffrey West one more time.
Thank you.